Hey student, Lars here. I want to talk to you about capacitors and resistors in the same circuit. Yeah, we're going to apply them. So we've talked about capacitors, we learned a lot about them and how they work and what they do and the, what was it called again? Wait, the reactance. Yeah. But in this case, we're going to put a resistor together with a capacitor. And specifically, we're going to study in AC. Because we know that in AC, the reactance does this funky thing. It changes, right? Or the resistance to current in a capacitor changes depending on depending on the frequency. Okay, so let's continue with putting them together and see what this looks like. Okay, so I want to talk to you again about resistance, or specifically total resistance in the circuit. Yeah, let's think about that. Okay, what's the total resistance of this circuit? Okay, so we know that this is R, and that's XL. Now, this guy is in ohms. We measure resistance in ohms. We also measure this in ohms. Okay, so easy. The total resistance is obviously this. Okay, so RT equals R plus XL, right? No problem. Actually, there's a problem. So the thing is that if this were true, the resistance, you know, it would just be weird because although this is in ohms, this guy is, well, it's out of phase, right? Let's take a look. I did this. Okay, now, I put this stuff on the board. Now look at the phases of a resistor and a capacitor as far as the resistance to current goes. If we actually look at this, we know that the current and the voltage across the resistor, they do this, they're in phase. But the current and voltage across this are different. So if we define R, right, using Ohm's Law, which is actually V over I, so resistance is V over I. Now, we also look over here. So in both of these, resistance is still V over I. But the problem is this. Let's study the capacitor and the resistor with a phase diagram. Okay, let's take a look. Okay, now if we were then to say the voltage drop, okay, the voltage drop across the resistor looks like that. What does the voltage drop across the capacitor look like? Well, it's out of phase. Now, the current just happens to be the same. So if we did a current diagram, it would just look like this. IR and CR, no. and IC, right? They're in phase together. They're fine. They're cool. Because the current going in and out of the resistor, remember it's going this way, is also going in and out of the capacitor at the same time. It's not like current goes in one at a different rate than the other. The current just flows through the circuit. Okay, so let's get rid of this. And let's take a look at this. Okay, I'm going to do the voltage drop across the resistor is right here. The voltage drop across the capacitor is out of phase. Good with that? It's actually 90 degrees out of phase, isn't it? It's not working. So it's 90 degrees out of phase. So there's a problem here, right? So we can't actually say this because this resistance here and that resistance there, oh, they're out of phase. Yeah, they are. They're 90 degrees out of phase from one another. So to actually add the resistance, we have to use this kind of thing. We have to use a phasor diagram. Okay, so where's my eraser? I'm going to use this. Cool. So what I'm going to do is I'm going to draw how we look at the resistances in this circuit. And I'm going to erase this because that's wrong. Okay, ready? Here we go. Now, we know that the voltage drop across the resistor looks like this. So also the resistance across the resistor looks like that. We know the voltage drop across the capacitor looks like that. So the resistance across the capacitor, or the resistance of the capacitor, is also like this. Okay, here we go. So now we call that, what do we call that again? XC. No, XL, yes, XC. XL is actually, we'll study that next week. Okay, so we know that's what's going on. When we add them together, what is that? Is that a vector diagram? It is. Okay, so when we add them together, we end up with this. What do we call that? Total resistance, right? No. We call it impedance. And that's actually a Z. I think impedance is so cool because it's a Z. So that's cool. So that's what's going on. This is actually how we add the resistance. And you know what? If you wanted to do the math for this, how would you do that? Let me just throw this over here. Are we good with that? I mean, you're allowed to do that, right? Vectors and stuff. So how do you actually calculate the length of this compared to the length of that and the length of that? Do you see a formula in there? Let me put a right angle in it, and maybe you might get it. Is that a right angle triangle? Does the square of the hypotenuse equals the sum of the squares of the other two sides in a right angle triangle? Yep. So this is what we do. We use the Pythagorean theorem, and we do this. Z equals the square root of that squared plus this squared. So r squared plus xc squared. I keep putting xl's. I gotta stop that. I'm talking about capacitors. So yeah, pretty simple. Okay. Now, how would we find the angle here? Because is the angle important? Maybe. Let me just take a look. Let me throw an angle down here anyway. Okay. Now, well, that's not very good. There we go. That's more pretty. Okay, good. Now, how do we find the angle? Yeah. The inverse tan, right? Remember tan was what? Opposite over adjacent? Something like that? Yeah. Okay. So, the angle is this. So, the angle, let me write this over here. The angle equals tan inverse of opposite over adjacent. So, the opposite is this xc. xc? Yeah, over r. I almost wrote XL again. Okay, so now that's what the angle is. Now, does the angle matter? Well, doesn't the angle actually have to do with the frequency? Let me write frequency on here. We don't know what the frequency is, but if the frequency increases or decreases, if the frequency changes, the length of this line changes. Oh yeah, that's right, because the reactance of a capacitor is dependent on the frequency. So depending on how we change the frequency, this thing goes up and down. Do you know that when you lower the frequency, that gets longer? If you raise the frequency, that gets shorter. So, oh right, that angle will change. So the angle and the length of the line are dependent on frequency. It's pretty cool. So that's actually how we find out the total resistance of the circuit. We call it impedance. So I have this example on the board because I want to talk to you about Ohm's Law and how it works in these circuits. Now, regularly, we know that V equals IR. If I want to calculate I, what would I use? I mean, would I use the R? Well, I need the total resistance of the circuit. The total resistance of the circuit is the impedance. So I've calculated it here. So you just throw that right into Ohm's Law. You can't throw just this in or just that in, but for the total. But you can very easily throw that in. So if I wanted to know I equals V over R, no. I equals V over Z. Pretty cool, eh? Just throw it in. So you just do that, and my voltage is 100 volts, and this is 1.12 kilo ohms, and I believe that, I got it in my calculator over here. What's the number? 62.69. I just lied to you. It's 82.69. So 82.69, and because my calculator is already in engineering notation, which yours is, right? I get this number, and then I have it times 10 to the negative 3, 10 to the negative 3, and then, or I, of course, can just write milliamps. So my point here is that Ohm's Law works with all of this stuff as long as you use that. Let's talk about Kirchhoffs laws. So when we're looking at a series circuit, we talk about Kirchhoffs laws and we jump right into voltage, right? So, I want this one. So when we're looking at voltage, we know actually Kirchhoffs voltage laws, actually they work very well here in this series circuit. And we know that Kirchhoffs voltage laws work just fine for AC, so we don't have a problem. So, if we had the voltage drop across that, and we had the voltage drop across that, in this case, those would add up to 100. No problem. We're good. We're golden with that. So let's see if we can apply this to something. Can we use the voltage divider rule here? Yeah, we can. Let's just call this VXC, because it actually is VXC. If we wanted to know the voltage drop across this guy, we could use the voltage divider for this. But watch what happens here. It's something a little bit funky. Ready? Here we go. So we know that VXC equals V source times some ratio, right? Because that's what voltage dividers are all about. We are going to take the resistance of this, which is really the reactance, and the resistance of this, and we're going to compare this to the total. And we know that's going to give us a ratio, and then we just multiply that by the voltage source, and we get how much of this guy takes up of this stuff. Okay, so now we know that this is going to be like this, XC. What's that? Well, it's regularly RT, right? In this case, it's Z. Cool, eh? Now, knowing this, we are now able to get this value, but wait a second. This guy is dependent on frequency. So it seems as though, does this make sense? Depending on the frequency, the voltage division across these guys is actually different. It is. It's really cool, depending on the frequency. Now, let's just analyze this one. If I had a low frequency, let's say go really low and really high, like look at the extremes, okay? So if we had like a really low frequency in this particular situation, would the voltage drop across these two be shared more over this guy or over this guy? Now, you remember, inversely proportional, right? Yeah. Reactance and frequency are inversely proportional. So if the frequency is really low, this guy is really high. No, that's the wrong number. I had that up there from before. Don't look at it. If this is really low, then that's going to be really high. Sorry, if the frequency is really low, that's going to be really high. So this is going to be taking more of the voltage. So what actually we do is we use this principle to filter out certain frequencies. Check it out. If I put a particular frequency in here, or a whole band of frequencies, a whole bunch, like music. Like, what does music have? A lot of frequencies, right? Music's got the bass, right? Yeah. And then, like, if Freddie Mercury's singing, it's got really high, right? But how do you actually, if you had like a bass amp, what would you do? How would you like just put where's my harmonica? I don't have it. Okay, that's mid-range, right? A harmonica's mid-range. What if you wanted to just filter out the mid-range and just like stick that into one of the speakers? If you needed to, let's say, filter out just the bass, you would use one of these circuits. You actually put all of the sound, all of the frequencies, the myriad of frequencies through this circuit. And if you did that, you would find that only the low frequencies would have a high voltage drop across this. That's true. It's pretty cool, dude. It's actually really cool. So then what happens here is that we then have a high voltage drop across here. We can take that voltage drop and we can then stick it into an amplifier, and then we can put it into a bass amp, or maybe a mid-range amp, or maybe a high amp, right? Pretty cool. So this is actually what we do for filtering out frequencies. Okay, let's do some math. Let's do an example. Okay, let's talk about the frequency response of this circuit, how this circuit responds to frequency. Now, just so we back up a little bit, this is a low-pass filter, so we're studying the low frequencies with this. We don't really care about the high frequencies, but let's take a look at what happens. So, if we were to take a look at this, we need to study it on a graph, right? And this graph that we're going to use is actually a semi-log graph, in that it's got log on this side. It's only one scale is log. If it was a log-log graph, it would be log and log. But it's a semi-log, so only one of them is semi. So let's take a look at it. What are we going to study over here? This is actually going to be the gain. Yeah, and what is it? That's A. Yeah. Just quickly, we will go over gain in a minute, but gain is V out over V in. That's a T. That makes sense? It's the gain? Okay, so as the gain changes, okay, we can see this response. Now let's take a look. What goes on here is this. This guy is going to do this over time. That's what the frequency response looks like for this particular circuit, that low pass. Okay, so as the frequency gets lower and lower and lower, the gain gets greater and greater, and as it gets higher, the gain drops off. And that's good, because we don't want any of these frequencies. Now, at some point in time, we have to decide, where's the cutoff? Where's the point where, we don't want any more? How much of this is usable? Well, we can say that maybe like 70% of it is usable. Actually, there's a number that we use that you might recognize. It's 0.707. So when the gain gets to 0.707, and you might know this, but that's actually minus 3 decibels. We don't need to get in decibels. Very cool things though. Now gain doesn't actually have a unit, so I'm not going to actually put any units here. This is frequency. We're good with that. What's going to happen here is that at some point in time, when the frequency, by the time the frequency increases, at that point where the gain is 0.707, we call that the corner frequency. Okay? And we do this. Frequency, corner. So it's the cutoff, or the corner frequency. And at that point in time, we don't want any of this anymore. And you know what? Anything after this is going to be severely attenuated. So it's going to be diminished. I want to do the same thing for like 10,000 hertz. But before I do that, what I want to do is actually want to study the impedance triangle here. Let's take a look at those vectors again, right? So in this particular situation, when we did that calculation, we found that it was like 50. So now wait a second. XC was 15K. It was plus 15K. So our impedance triangle is going to look like this. If that is 1,000 ohms, which is R, right? This is going to be way down here, like way down there. So that is actually going to, our impedance triangle is actually going to look like this. Our Z is going to, this angle is going to be really huge. And that's kind of what we want for a low pass filter. Because we want this guy to be much bigger than that guy. So that's the impedance triangle for this. But for now, actually, let's get to the next step and study this with like 10,000 hertz or something like that. Cool. So, and we'll actually look at the impedance triangle there as well. Cool. So if I had 100, instead of 100, I'm going to put 10,000 hertz. Cool. Redo the math. What I need to do is I need to calculate that guy. XC equals 1 over 2 pi, in this case 10,000 hertz, times 0.1 microfarads. And XC in this case equals, that was, this number is really high. So the reactance is going to be really low, and it is. Compared to our last number, this is really low. It's 159.15 ohms. That's pretty low. Now XC is also going to be low, but it'll be a lot higher because it's got that 1,000 in it. So let's do the XC. Sorry, the Z. Okay, cool. So Z equals, that's R squared plus XC squared. And the answer to that is, I've got it here, is 1012.59 ohms. Now we can see, let's do the impedance triangle. We can see that this guy and this guy are like really different. So when we do our gain, if that's on top and that's below, the gain's going to be really small. So the impedance triangle is going to look like this. I'll just stick it right in here. I know that the same length is going to be here for R, which is 1,000 ohms. This guy is, I don't know, about that, probably not even this. Because this is only 159 ohms. So look at that. And this angle is going to be really small. So it seems as though if I want a really high gain with a low pass filter, if this angle is really big, I'm good. If it's really small, it's not. Where is this on the picture anyway? First of all, let's actually do the gain so we can calculate where this is here. So the gain in this case, which again is A, which is equal to XC over Z. Now I calculated that already. The gain here, was it 157? 159? Yeah, that was 159. And this is 157. It's pretty small. It's 15.7%. It's not very much. Cool. So if we look at 15.7%, that's 70%. 15.7% over here. So we're talking like way, way, way past. This is 10,000 hertz. That's way past our corner frequency. That's way up. This will be extraordinarily attenuated. So even if it's a really high amplitude, right? So whatever sound it is in the music, or whatever the frequencies are coming in, lots of them are coming in. That 10,000 hertz even though it's really going to have a high amplitude, let's say it's really, really high, it's a loud scream or something, that 10,000 hertz, it really won't be part of it. It'll be actually 15.7% part of it, but that's not very much. The way I remember high-pass filters is this. It's kind of the high and low concept. If I put my capacitor up here and my resistor here, then my capacitor is high. Yeah. So when the capacitor was down here, it was low, so that's a low-pass filter, and this is a high-pass filter. Let's just take a look at this. Now, if I were to put, say, a really high frequency in here, what would that be? What would the reactance here be? It would be really low. No, sorry. Yeah, it would be really low. If I put a really high frequency in here, this would be really low. So that would be really low, and then that would mean that this guy would be higher than this. Let's say it was 10,000 ohms. Let's make this 10K. 10 kilo ohms. So now, at really high frequency, this becomes a very low number. So if that's a low number, and we're looking at like a voltage divider, then this guy, a lot more of the voltage is going to drop across this than it is this. So a high-pass filter, thank you very much, is essentially we put the capacitor up here so that when it is high, the impedance will be really, the reactance, will be very low, and that means that this guy will see most of the voltage. Now the formulas are pretty much exactly the same, maybe just a little different. So if we study the impedance triangles for a high pass and a low pass, we see some interesting things. They're kind of opposite, right? So what we want out of a high pass filter is an impedance triangle like this. We want actually a lower impedance and a lower angle, because really we want this to be a much larger number than that. Cool, because in a high pass filter, if the frequency is high, what is that really high? No, it's really low. The reactance of this component is really low, so it'll be lower than this. If that number is big enough, right? You've got to design your circuit. So we know that in a high pass filter, this becomes really low, and then the voltage drop across the resistor is going to be much higher than the voltage drop across this. For a low pass filter, we know that when the frequencies are really low, this is going to be really high. So the voltage drop across this is going to be higher than the voltage drop across this, because my XC is going to be higher. Now, if we actually do the math on this and we look at the voltage drops, we know that Vs is R over Z. Cool, I think that makes sense, right? The output, the voltage out, is actually the voltage divider formula. So it's actually Vs over this ratio. Now over here, the voltage out is Vs times that ratio, because it's XC over Z. Cool. So that brings us to gain. How do we calculate gain? Gain is A, which is weird, right? Cool. Over here, A equals the V out over the V in. Now, we can kind of expand that a little bit and use actually the voltage divider formula, because I want to get a better formula for actually gain than finding the voltage, because then I have to calculate the voltage drops all the time. Cool. So if we take a look at this, I know V out is Vs times R over Z. Now, over V in. Now, V in, if we use the voltage divider to calculate V in, it kind of ends up weird, but mathematically it's correct. We know that it's Vs times Z over Z. Yeah, it's mathematically correct. Cool. So now if we take this, we can get rid of our Vs's, and we end up with RZ over Z over Z, and that equals R over Z. Does that make sense? Cool. So what I can do is this. I can actually say that this also equals R over Z. Now, that's specific actually to a high-pass filter. If we do the same thing for a low-pass filter, we end up with this. A equals V out over V in. Now, the other thing is we can switch this around and do the same formulation here, but we're not going to end up with the R. We're going to end up with the XC. XC over Z. See, the gains are a little different, but technically they're looking at the same thing. They come from the voltage divider, and they're finding the voltage drop over this. the voltage drop over that. So we're actually, boiling it down to resistance and inductance. No, reactance. Yeah, that's better. Does that make sense? So we've looked at filters that attenuate high frequencies and don't attenuate low frequencies. So those are low pass filters. And then we've dealt with high pass filters that attenuate low frequencies, and the high frequencies seem to just come right out of them. But what about like that mid-range? I talked about that at the beginning, right? As far as like instruments go, right? The low range is the... Sorry, yeah. Hey, that? If we put that through a high-pass filter, we wouldn't hear it. And then the high... Right? We wouldn't really hear that either. If we put that through a low-pass filter, it would go in, but it wouldn't come out. Now those mid-range... Right? Those mid-ranges, if we put them through a mid-range filter, they will come out. So how do we draw a mid-range filter? Like, what is it? Any ideas? I think you might have an idea. It's pretty simple. You just start, you can actually do this either way. You can start with a low or a high, but you know what? I'm going to start with this guy, which is a what? A high. Oh, that resistor didn't go very well. Okay, now I'm going to do this. Now, I now have a low pass. So I've got a high pass filter and a low pass filter. And depending on these values, I can target these values. Actually, do you know what? With that like corner frequency thing, I can actually get the corner frequency for this, and get the corner frequency for that, calculate it, and we can just simply do this. I'm going to draw our semi-log, and I'm going to draw what this guy looks like. It starts with the high pass, and then it goes high. And then we get the low pass. Sweet. That's what it looks like if we actually do this. So as far as like the math goes, I need my red. When we look at their corner frequencies, and we dial in the 0.707, we're right there. And that's the corner frequency, and that's the corner frequency for the low, and that's corner frequency for the high. So we can target any specific frequency we want. One application of this that actually you probably don't know this so well because you don't see them around anymore, but they were around a lot in the 70s and the 80s, are these things. Here's your stereo, right? Volume dial and your channel dial. And that out here to your speaker, right? What was this guy? The sliders, remember that? The equalizer had a whole bunch of sliders. I still got one of these kicking around somewhere in some closet. But they had actual physical sliders that went up and down. Each one of these sliders was connected to a band pass filter. And then each one of these was a potentiometer, a linear potentiometer. And what it did was it just targeted a certain frequency, took that frequency, and depending if you put it up there or up there, it actually amplified it or attenuated it. So you could quiet it up a little bit or turn it up. So these are pretty cool to play with, and actually, you know what? Does that make a lot of sense now how these work? Band pass filters, low pass filters, high pass filters, very cool. And what do we use? Yeah, dude, I was going to point at the capacitor that's not here. Oh, draw it. We use capacitors. Very cool things. So what I want to do now is actually take a look at maybe a circuit in action. So I designed this cool circuit. It's actually got two filters in it. Let's check it out. This switch gives me the option of switching back and forth between the two circuits. And I've got a low pass over here and a high pass over here. I've also put a switch in here so that I can just kind of bypass these filters completely and look at the raw waveform. So the raw waveform is actually coming from two frequencies. Check it out. So I put actually two frequencies in here. This is 12 kilohertz. That's 100 hertz. What I want to do is use these filters to see if I can take a look at this and take a look at that. So I have to design my circuit. I'm going to take these out. I'm going to design my circuit, and essentially what I need to do is figure out what those numbers should be. Yeah. So what I'm going to have to do is really try and figure out what it is exactly what I want to filter. If we take a look at the frequency response for both of these, so the blue is a low filter, and the yellow the orange is the high filter, okay? what I'm going to do is I'm going to say, let's take a look and see if we can filter out 100 hertz. And also, that's over here, this guy is going to be 12,000 hertz. Okay, good. That doesn't look like a hertz. Okay, good. So, what I need to do is, I need to figure out now what my corner frequencies are. Yeah, because I'm designing my circuit, and I have to figure out what the capacitors are, and they will define my corner frequencies. Now, I need to figure out a corner frequency right here that is a little bit past 100. Let's go for like 333. So, let's say this is 333 hertz, and this guy, let's make this 7200. 7200 hertz. Cool. So what I can do next is I can actually do the math and calculate what the capacitance is required to make those corner frequencies happen. So we've got C1 and C2. So for C1, what's the formula? Like what's the formula? Well, let's take a look at this. That's the frequency. That's the formula for calculating the corner frequency. So actually, I know the corner frequency. I just want my capacitance. So I can rearrange that. That's going to be this over 2 pi, and then I'm going to put my corner frequency in and my resistance. Now, if I actually plug these numbers in, I'm going to go 2 pi, and then the frequency for my corner frequency is 333 hertz times 1,000 ohms. Cool. Now I've calculated that, and that comes out to 0.477 microfarads. Cool. Now, if I go ahead and calculate the C2 in the same way, C2, that is actually going to equal 22.010 picofarads. Cool. I have to choose my capacitors. So what am I going to choose? Am I going to go and actually get a capacitor that's exactly 0.477 microfarads or 477 picofarads? I don't think so. But does it really matter? It doesn't actually matter. Check it out. If I were to use a 470 picofarad, which is readily available, is it going to be okay? Am I going to get exactly 333? No. Am I going to get pretty close or very close? Does it matter? Not really. Because I'm looking for 100 hertz, right? I want to stay way below 333. If that number is 327, it doesn't matter. Okay, same with this. Am I going to find a 22? Well, maybe. I might have one in stock, but I got two 10s, right? 210 picofarads, so I can put those together, and I can end up with 20. That's going to work for me as well. So I'm going to put those numbers down because, you should label your circuits. Okay, cool. This guy is going to be 0.47 microfarads, and this guy is going to be 20 picofarads. Cool. So if I put those together and build this circuit, it'll actually work. I wanted to look at gain. It does the calculations, which you can do. They're pretty simple. We know how to calculate gain for each of these things. So I've actually got the gain here for 100 hertz being pretty good. This is 95.6% or 0.956. And over here, we're not quite as good, but still, that's pretty good. We're over the 0.707. So that's a good number, and that's a good number. These, I think, are good values. They're going to work for us. Now, let's actually take a look at the frequency response. Pretty cool, eh? Yeah, and as you can see, that actually works out. Now that's the actual frequency response curve, and as you can see, our math then works at it. And you see the where you go for 100. See where 100 is? Yeah, that's where you're getting this number. And over at the 12,000, you have it's just a little bit lower, but that's pretty cool. Anyway, let's build a circuit. So here's our filter circuit. I have the option of looking at it raw, like that, or I can look at one filter or the other. That's the high-pass filter, that's a low-pass filter. This is my 0.47 microfarads, and these are 10 picofarads together in parallel, so I now have 20 picofarads. Cool, so now let's take a look at the raw waveform. That is the 12 kilohertz, and also, if I go over here to the other channel, that's the 100 hertz. The 100 hertz is that, the actual waveform that you see there, the big one. And then the one that seems a little thicker, what that actually is let's go over to here to channel. Let's actually change that a little bit. Oops, daisy. frequency. Cool. So now let me just do this and you should see it. See that? There it is there. What we're going to do is we're going to filter that out. I'm going to turn it back up to 12 though, because our filter is designed for 12. And so that's both of them. I'm going to turn this off. Now let's just look at the low pass filter. So as soon as I turn the low pass filter on, we're not going to see that high frequency. There it is, ready? Cool, eh? It's nice and clean. Now if I turn the low pass filter on, sorry, the high pass, look at this. Now I'm getting that high frequency. I'm actually going to take this and put this in here. So I don't have to use the switch. Now let's actually look at this. If I take a look at this, look. Ooh, there's that frequency. That's that 12. That's 12,000 hertz. Pretty cool, eh? So we've learned about capacitors and resistors, and we put them in circuits, and we can do some pretty cool things with them, filter stuff out. There are many more applications for resistors and capacitors in circuits, but right now we're just looking at filters. You can go way beyond filtering out just music. You can filter out signals from all sorts of information that's coming in, like sensors and stuff, and also in tuning circuits for radio frequency tuning. They're like huge in there, and you'll find that there are frequencies all over the place, and we really have to tune them. So they're pretty cool. It was fun talking about all this stuff and building the circuits, and I hope you got something out of it. Thanks for watching.